Hi everybody, here's our video on rational function notes. This is going to be used to fill out your blue sheet which you got in class a couple days ago. I'm sorry for the video delay. I meant to do this yesterday and I'm just making it now on Wednesday evening. So it's due Friday. So you'll come to class Friday with your blue sheet filled out and you'll be using that on Friday in order to graph these by hand. So we just finished polynomials, remember, and polynomials lead directly into rational functions because the definition of a rational function uses polynomials. So if I'm going to actually do a formal definition of a rational function, what it is, so a rational function is the quotient. I remember quotient means division. So the quotient of two polynomials. So just picture all those polynomials we just spent a month factoring and graphing. If you take two polynomials and you divide them, you have a rational function. So there are tons of different kinds of rational functions that you can get. The most basic type, if you look in a book, your textbook definition will be p of x over q of x, where p and q are each polynomials. So one example of a typical rational function that you'll be graphing by hand soon is x squared minus 1 over x minus 2. Now you might be looking at this saying like, oh, well, that's not a polynomial. This is just a line. But a line is a polynomial. It's a polynomial of degree 1. And then here we have a quadratic, but a quadratic is a polynomial of degree 2. So I have two polynomials divided by one another. So that is an example of a rational function. You could also have something very simple on top, just one term, and then you could have a trinomial on the bottom, a bunch of terms on the bottom. Now, one thing to remember is when you're graphing a rational, we said this word before, but let's just remind ourselves here because there's a decent amount of vocabulary here. The shape is usually a hyperbola. I'm saying usually because we will be graphing several types of these, and they are not always hyperbolas, but the entry-level ones are going to be hyperbolas when you graph them. Okay, so the main difference between a polynomial and a rational is domain. So the domain of a polynomial is always going to be all real numbers. All that means is whenever we graph this, they went all the way to the left, we did something in the middle, they went all the way to the right, like every single x was hit for a polynomial. But whenever we do a rational function, the domain is not going to be all real numbers. We'll have some kind of domain restriction. And remember, we can never divide by 0. So the domain restriction, you're going to look at your denominator and think, what would make us divide by 0? Because dividing by 0 is the thing that's not allowed in math. So our rationals are only defined when the denominator is not equal to 0. So the way that you'll get the domain of your rational is you will exclude the x values that make the denominator equal 0. So make sure you're writing this down with me as I go. And the thing is, the x values that are not x values not in the domain, so all those x values that do not work, those are going to end up being your vertical asymptotes. Are the vertical asymptotes. You could have one vertical asymptote, you could have two vertical asymptotes, you can have as many as you want here. One thing, in case you're interested in where the word asymptote comes from, because all rational functions have some kind of asymptote. The Greek word asymptotos is where the word asymptote comes from. And the Greek word actually means not falling together. And if you picture what an asymptote does, like let's say I'm just going to draw a random rational function right now. So let me draw some asymptotes. Whenever you draw them, you get close to your vertical asymptote, you get close to your vertical asymptote, but this piece and this piece are always separated by my vertical asymptote. These two pieces will never fall into each other. So that's where the word comes from, in case you're interested. Okay, so like we talked about before, the asymptotes are imaginary dotted lines that the graph approaches. Asymptotes can be written using limit notation, actually. Now, some people get intimidated by limits because it's kind of like a calculus thing, but they get introduced in pre-calculus. So this is the first time you're going to see limit notation. So another thing I want you to add here is, while we're on the topic of asymptotes, polynomials were continuous functions. Rational functions are not continuous. So your graph will be discontinuous at the asymptotes. I should say vertical asymptote. Vertical asymptote. All right, so here's the graph we're going to do now. And before we do anything else, I want to get some values that are really close to -4. The reason I want to get really close to -4 is, what if you tried to plug -4 in for x? The numerator would be fine, it'd be -8. But if I try to plug -4 in right here, I would be dividing by 0, which is not allowed. So I'm picking numbers that get closer and closer to -4 from the left, and closer to -4 from the right. And I have my calculator here to get some values quickly. So I typed in my function. I'm using parentheses around the top and bottom. Here's a graph of what we're looking at. And to get really quick numbers, I'm going to do value, and I'm going to type in -5. Notice I'm at 10. So write that down in your table, 10 for -5. If I go to value, and let's do number 1. This time, let's get even closer. Let's do -4.1. Now I'm all the way at 82. I'm so high up on the graph that I can't even see it. If I do it one more time, and let's do like -4.01, I'm at 802. I'm way up on the y-axis here. Now let's say I decide to go on the other side of -4, like -3.99. That's also on your table. We're at a really small negative number this time. So right here, you have to remember, is -4, where my mouse is. -3.99 is just to the right of that, and I'm way on the bottom. Then let's do 2 more quick, -3.9. We're at -78, so we're still really far down, but not quite as far down as we were before. And then if I'm at -3, I'm only at -6 here. So if we go on the table, here I put in all the values that we got. And remember, -4 is the dead zone. That's the DNE does not exist in the error, because if you put -4 and you're divided by 0. So first we were -5. We're getting closer and closer to -4 from the left side. So one thing you're going to have to know is talking about from the left and from the right. So here's -4. If I'm coming from the left, that would be numbers like -5, -4.1, -4.01. So here. If I'm coming from the right, that means I'm starting on the right side and then getting closer this way. So numbers over here are from the right. So let's answer this question here. What happens to the values of g of x, the y values, as x approaches -4 from the left? That'd be over here. So coming from the left, the y values are getting huge, and they're approaching infinity. They increase towards infinity. And we'll write a limit for that in a moment. Whenever I approach -4 from the right, so that would be like over here, so -3, -3.9, -3.99, my y values got larger in the negative direction. So here we were approaching negative infinity, and we were decreasing. All right, let's write our first limits. So here's our limit notation. Whenever you write a limit, you're always going to start with LIM. This is an L for limit. And you're always going to have the limit of some function. So this is the limit of g of x. And the limit is always going to equal a y value right here. So this box is always going to be some kind of y value. That's what the limit is. Right under the limit, you're going to put x approaching. So right here, x was approaching -4. And for the first one, to say you're approaching from the left, you always put a little negative after the number. So I'm approaching -4 from the left. And then what was the limit? Like, what were the y values doing? Well, they were approaching infinity. So my limit's infinity. The next one, I'm going to do the limit of g of x equals some y value. This time, let's do the limit as x approaches -4. Let's come from the right, from the more positive side. So you do x to the approaching -4 from the right. And as x approached -4 from the right, the y values got smaller and smaller towards -infinity. So the limit is -infinity. So I know it's the first time you've seen it, and the notation might seem a little uncomfortable at first, but you'll get used to them. Okay, if I want to do larger and larger values, I'm going to do the same exact thing I did before, except I'll do it for like 5, 10, 100, 1,000. When you type these in the calculator, you can do that on your own. I'm going to fill in the values we get. Here I have a table for x values that are getting larger and larger and larger. So starting from 5 all the way to 1,000. So this is very different than up here where we had numbers very close to the vertical asymptote of -4. This time we're starting at 5 and going all the way to 1,000, starting at -5 going all the way to 10,000. So here I started at 5 and went really, really far this way. I started at -5, -5. I went really, really far that way. Now let's notice what's happening to our y values. I go from 1.1, 1.4, 1.923, 1.992. If you kept going, these numbers will get closer and closer to 2. And if you went on a graph, and if you remember how we were hitting the right arrow key after you hit trace, if you held on to the right arrow key, we would be leveling off at a y value of what appears to be 2. Similarly, if I start at -5 and I go left forever and ever and ever, you can see the fractions here. Your decimal gets closer and closer to 2 as well. So as x, what happens to the values of g? As x takes on very large positive y values, g of x increases towards 2. So the numbers are getting bigger. Here, as we get to close to very large negative values, our y values are actually decreasing. So g of x decreases still towards 2. So you're going to need to be able to draw a graph given just asymptotes. So here, this is giving us our horizontal asymptote. By definition, a horizontal asymptote is what happens as you go towards infinity and towards -infinity. So if we want to write a limit for this, let's write our third and fourth limits here. One limit per statement. Here I have a limit of g of x as x approaches something. Okay, so let's look at this table right here. What is x approaching? So x is getting bigger and bigger and bigger. X this time is approaching infinity. And what's y getting closer and closer to? Y is approaching 2. So remember, your y value is your limit. So now let's do it for the last table. In the last table, my x's this time are approaching -infinity. They're getting smaller and smaller. The y value that the limit is approaching is still 2. So let's do our graph here. I have a horizontal asymptote of 2. I had a vertical asymptote of -4. So x equals -4, y equals 2. And our graph was, as we approach 4 from the right, our graph got smaller. The y values went down. Oops, that's a little bit too close to the asymptote. It's going to be, now you want to draw it close but not touching. And then as we approach -4 from the left, our y values got really, really big. As the x is approaching infinity, our y values increase towards 2. And as our x approaches -infinity, the y values decrease towards 2. Like that. So I'm going to get as many of these notes in on the back as I can. I have like a minute left. We'll get a couple things in. You're going to be drawing rational functions by hand. So let's start the notes. We'll finish in class. The first steps that you're going to want to do are simplify and factor, if possible. After you've simplified and factored, you're going to want to find your intercepts. We want to get our y-intercept and our x-intercept. Remember, to find the y-intercept, something like this, you always plug 0 in for x. And to find an x-intercept, something like this, you're going to technically set y equal to 0, which is the same as setting the numerator equal to 0, and we'll talk about why. So get these examples written down. We'll do them in class together, and I will see you tomorrow.